Hi, my name is Sean Perry. Welcome back to a lecture series on Calculus 3. Today we're going to be talking about some preliminary vector operations and some of the most important things we can do with vectors. We'll be talking about writing vectors in terms of a basis, namely the orthonormal basis that you get from the axes. We'll be talking about the dot product, perhaps the most important thing you can do with two vectors. We'll be talking about projection and how to tell how much of a vector is pointed along another vector. And we'll be talking a little bit about unit vectors today, which is scaling down or scaling up your vector so that it has length 1 but points in the same direction. So for those of you without the time to listen to the whole lecture, here's a quick TLDR on everything that I'm going to talk about today, or almost everything. Please check the notes that I'm going to post along with the video, and let's begin. So to start with, two of the most important vectors in R2, and all of the talk today is going to be about second dimensional vectors. Oh, that doesn't show up very well. Hang on a second. We're going to be talking about two-dimensional vectors majoritively. I'll make another follow-up video about three-dimensional vectors and n-dimensional vectors and how all these operations kind of play into those arenas. But for now, let's just think about the plane. And we're used to thinking about the plane in terms of the coordinate axis, and now we are orienting points in a certain way where we are directing line segments from the origin towards some point. Now, the two perhaps simplest but most useful vectors are the basis vectors that you get from these axes. So every time you define an axis, you have to tell me where 0 is, and you have to tell me where 1 is. And we could create a vector that points from the origin along this axis, in this direction, to 1. And in component form, right, that would be the vector 1, 0. And we give this vector a name, I hat. So it's an I, but instead of a dot, it has a little caret or a hat on top of it. We give hats to vectors instead of, the usual arrow that I've put on top of them. We give a hat to show that it only has length 1, or specifically has length 1. So in this case, it's pretty easy to see that it has length 1, right? It's only going in one direction, and that segment has length 1. And correspondingly, if we went up along the y-axis a certain amount, let's say 1 unit, then we'd also define a vector going this way. And this will get the name j hat. That is to say, the vector who's defined in component form 0, 1. So a couple nice things about these, as we noted, they are unit vectors. They are orthogonal to one another. And orthogonal or orthogonal is just a synonym for perpendicular, or at right angles to one another, or having an angle between them of 90 degrees, just like the axes do. Additionally, they are a basis. And we'll talk about what that means. But briefly, it means that any vector in the plane can be written as some kind of scaled sum of these vectors. You scale the vectors, you sum them, and you can write any vector in this form. So let's take a look at that. So let's get a axis on here, and I'll show you what I mean. let's say that we're given some vector u, and let's say in component form it had coordinates x, y for its endpoint. In other words, that your length along the x-axis was the number x, and that the length along the y-axis was the number y. Well, what we could do is add up some scaled amount, some scaled value of I hat, right? We could multiply that by x. And this would give us the horizontal component of u, but now written as a vector. And likewise, for y, we could get a vertical vector by writing yj hat, and this would take the unit vector j and scale it by the right amount to get to the coordinate y. And if we were to do such a thing, we could write u in not its coordinate form, but in what I'm going to call basis vector form. So basis vector form is going to be written not as a coordinate such as this, but as a sum of the scalar product of two vectors. So let's write that. X I hat plus y j hat. And now we no longer have a coordinate here. We have instead a sum of two vectors, each of which has been scaled. And because we can take any u in the entire plane, any vector, and write it this way, this is what we mean when we say that I and j form a basis of R2. So now I want to talk just a little bit about other coordinate systems, because you've seen other coordinate systems before, right? When you were working with the x and y plane, as it were, you also had polar coordinates. And there's a use for polar coordinates here. I'm not going to go into its full detail, like writing them in terms of basis vectors, like r hat and theta hat. That will take a little bit more time to develop. But what we should remark is just the obvious stuff for right now. So let's say I have some vector u again. And maybe I define it component-wise. But we also know that just like points in the plane can be defined using the distance from the origin and the angle that makes with the x-axis, aka polar coordinates, for all points except for the origin, of course, who has no direction. It's sitting right here at the beginning. For all non-zero vectors, we can also describe exactly what this vector is in terms of some theta and some r, some magnitude of u, which is just this length of the vector, all this. And I'll keep with the double lines on each side indicating magnitude of the vector. But you will also see in some books, you'll see single bars to indicate that this is the magnitude of the vector. You'll see abs val used exactly the same way. And just another note on notation, I use the arrows on top of the vector because it's too hard to write bold units by hand. But in many, many books, you see vectors distinguished from scalars because one will be bold and the other will be regular, not bold. Okay, so the same way that you would normally use the Pythagorean type theorems to write the magnitude of u in terms of its components. And as long as we're, not going to take too much time to talk about the intricacies of arctangent and how exactly you get a angle theta from these components x and y, right? We should review our trigonometry for that. And I don't have time for all that review in these videos. They're long enough. We could, for certain values of x and y, talk about this in terms of arctangent of the adjacent over the opposite. Now, of course, that might require a little bit of tweaking if we leave quadrant 1 or quadrant 4 if we want to not be negative in our value but go between 0 and 2 pi. So quadrant 2 or 3 or 4 if we want non-negative angles. We're going to have to do something different than this, but this is a good rough approximation. This should develop your understanding a little bit about how you would get this angle from coordinates, right? Review your trig. But that's not really the main ideas that are going to get played very heavily in Calc 3. What's going to be more important, it turns out, for our purposes, is going to be writing the coordinates in terms of these angles and magnitudes, right? So here we have the magnitude playing the role of r, and from the definition of cosine, right, we have that this is cosine of theta times the magnitude, giving me x. And likewise, I could get y the same way, magnitude times sine of theta. And from this, we have a way of taking information given in terms of a magnitude and an angle, which is often, for example, how your physics problems are going to be set up. They're going to tell you the angle of the force with respect to some coordinate system, and they'll tell you the magnitude of the force. We could also write this in terms of our orthonormal basis of our coordinates I hat and j hat, right? So we could then say that any one of these u could be written as follows. Its magnitude times cosine of its angle I hat plus its magnitude times the sine of its angle j hat. And we would call these the x and y components of u. So let's look at an example of applying this. So let's say we knew that the magnitude of a vector was given by, I don't know, some number, 7. And let's say that we also knew that the angle that it made with some axis, say the x-axis, was 120 degrees. And we could draw such a thing, right, which often helps us to at least visualize the problem. Right, 120 degrees from the x-axis brings us a little bit more than 90. And a magnitude of 7 indicates this overall length here. And we might want to figure out what component of this force, shall we say, points in the x direction horizontally and what direction is oriented vertically. And to do that, we could simply decompose it into its basis vector form. So from x equal to the magnitude of u times cosine of 120, we would have that this is 7 times negative 1/2, right? Refresh your unit circle. And then y would be equal to the same, magnitude of u times the sine of 120. sine of 120 is going to be the square root of 3 over 2, and so we have 7 times the square root of 3 over 2. And simplifying this, we could take and write our vector u, there's u, in terms of its vertical part and its horizontal part. So its horizontal part would in fact be negative 7/2, oriented in the horizontal direction, plus 7 square roots of 3 over 2, oriented or scaling the vertical unit vector. And that's pretty much all there is to that. The reason that this is such an important thing to do and that it's non-trivial is that direction and magnitude are often how the problem will be given in a physics class, for example. And when we go to add and subtract vectors with one another, it's most easily done if we know parts that are parallel or perpendicular to one another. So in order to add and subtract vectors from one another most easily, it's often best to write it in terms of two vectors who are orthogonal to each other. So we talked a little bit about unit vectors just now as being vectors that have a length of 1. Any vector that has a length of 1 is a unit vector. And we can correspondingly take any vector we like and rewrite it in terms of a length times a unit vector pointed in the same direction. So specifically what I'd like to show, or like to show you the formula for, is how to take and rewrite any vector we like. Maybe I'll just keep that as xy. In terms of a unit vector, right? Or to get a unit vector from any vector. So what will such a vector look like, right? Well, let's say x is bigger than 1. I'll put a 1 right here and a 1 right here. Draw this little circle. Forgive the crudeness of my circle. But let's say this has radius 1, this circle. Well, all vectors ending on this circle have length 1. And in particular, the one which is oriented along this vector and ending on that circle is our unit vector. And to distinguish these vectors with arrows on top versus unit vectors, I will give that unit vector a hat. This is also true. We can also do this even if it's not greater than 1. But before I show that, right, before we talk about that, let's talk about how you would scale this guy down to have the right length, right? So if we wanted to have length 1, what I could do is divide by its own length. To wit, if I want u hat, what I'm going to do is take u and divide it by its magnitude. Now, what does it mean to divide? Well, I would have no idea if this was a vector, but norm down here is a scalar. I know how to divide by scalars. You multiply by its reciprocal, right? This is the same thing 100% as multiplying by the number 1 over u. So in particular, we can only do this. We can only make unit vectors out of non-zero vectors, or else this makes no sense. Scaling, doing scalar multiplication, which we know how to do, previous video, by u itself. And likewise, so really what are we doing here? We're multiplying by the reciprocal of its norm. You'll also see that using the other usual ways of writing a reciprocal, like with negative exponents or something like that. That's also pretty common, but it means the same thing. And if that is bigger than 1, dividing by something larger than 1 will shrink it. In the same way, if I had something shorter than 1, like let's say I had v, right? And v was some smaller vector, a tiny vector with norm less than 1. Well, then what would dividing by its length do? Dividing by something less than 1 makes it larger, and by exactly the right amount that we need. If I wanted v hat, again pointing in the same direction as v, but ending on the unit circle so that it has length 1, then this v hat is given the exact same way. There's literally no change in the formula. We're just going to divide or multiply by the reciprocal of its magnitude. And we talked last time about how to take the magnitude. We also saw a little bit of that in the previous slide. It's the Pythagorean theorem. Okay. So again, let's look at some kind of example of this thing in action. Let's say I had the following vector system. Let's say we had u, a vector of the following size and orientation. And I wanted to know, what is u hat? This is our question. So the first thing we would want to do is calculate the magnitude of u. And I've picked these numbers nicely, but in general, if we want a magnitude, we just follow the Pythagorean theorem. Here, of course, we're going to have a Pythagorean triple, but just to write it all out, the magnitude of u is given by the square root of its x component squared plus its y component squared. And this is 16 plus 9 is 25, square rooted is 5, and so the magnitude is just 5. In other words, the reciprocal of the magnitude is 1/5. And so all I have to do to calculate the unit vector is scale the original vector by 1/5. And remember, scalar multiplication, you just multiply each component, and we get 4/5 and 3/5. And so if we were to graph this, right, that would be something a little less than 1 on both cases, right? So let's just approximate it. Right? Here's 4/5, and here's 3/5. And they're proportional in the same way that 3 and 4 were. That means they point along this vector. And this would be our u hat. Okay. So that's what I wanted to say about unit vectors. Let's move on to one of the most important vector operations. Oh, while we're talking about it, I should at least remark a little bit. I say operations and functions as if those are different things. So it really depends on the nomenclature being used, by your professor or in your book. But one way to think about an operator is that it takes elements of a set. So it's a function. I'll call it O. And it takes elements of a set, perhaps one of them, but perhaps many of them, right? Maybe it has several inputs. It could have 2. It could have 3. And in general, it maps you back to something in that set. So a function taking several, well, perhaps several, let's say 1 or more, elements of a set and returning an element of that set. So operators you might be familiar with, addition as a numerical operator or multiplication as an operator, right? What do these things do? They take in two numbers and they give you a third number. So when I say a vector operator, I mean something that takes in a vector or two vectors or more vectors and gives you back a vector of that kind or something in the original set, which in our case is a vector space. A function, on the other hand, doesn't have those restrictions. It takes in any number of elements from any number of sets, and it gives you anything else from any other set, right? So for a function, is more general. A function f takes sets of perhaps many different kinds and returns another set, maybe of some different kind, right? There's no requirement about the inputs and outputs other than, of course, your old vertical line test, the idea that there can only be one output for a single input. If it is more general than that, it's called a relation or a multi-valued map or any number of other ways we could get more complicated than that. But that's all I wanted to say about operators. When we talk about operators, we're talking about things which take in one or more thing, and they give you the same kind of thing back. So our vector operators are going to be things which take in vectors and give you vectors. And yes, if you want to talk about numbers as being one-dimensional vectors, okay, cool, we can always do that. So in a certain sense, even things like what we'll see as the dot product are an operator of sorts, but wait, they don't actually necessarily give me a vector back of the same dimension. So I, personally, wouldn't call them an operator. I would call that a function, a real valued function. So now, instead of talking about this kind of thing where, the process of taking a unit vector is an operator, right? It takes in one vector and it gives you a vector back. It gives you a scaled vector back that has length 1. On the other hand, when we talk about the dot product, we're talking about a function, a real valued function. It takes in vector arguments and it produces a real value. How does it do it? Okay, so let's talk about the dot product. And I will be more general with the dot product later. I'll talk about it in the next video for R3 and perhaps Rn. But for right now, again, we're just going to be keeping things to 2 dimensions. So let's take 2 vectors, right? The dot product is going to have an input, 2 vectors, and its output is going to be 1 scalar value. And again, for this course, we're just going to be talking about real numbers when we talk about scalars. Okay. So let's draw 2 vectors up here. Call him U. Well, in my notes I called this one V, whatever. And let's say it has components as follows. So I'll give you the components x1 and y1. So this guy has an x component here and a y component here. And V, I'll call him x2 and y2. And so here's x2 and here's y2. And we're also going to want to talk about these this thing in terms of the angles between the 2 vectors. So let's also remark that they have angles and magnitudes, right? Like this has a magnitude of V double bar here, the norm of V. And this has a magnitude thus, right? And they have angles too, right? This one has an angle, I'll call him theta 2 to keep the 2's associated with V. and this one has an angle of theta 1. And before we really get going with this, let's note that there's also a third angle just kind of calling to us in this diagram, which is the angle between the two of them. So I'm going to call this one theta. And theta is simply, if I pick theta 1 to be the larger of the two, let's say that theta is equal to theta 1 minus theta 2. And you might say, well, hey, does it matter what order I pick them in then? And for the purposes of the dot product, it will not. But in general, it will. So in general, that is a consideration that's very important. Which one comes first? But this is going to turn out to be commutative. We'll see that in a second. So there are two ways that we can define the dot product. So one of them let's say u dotted with v, and we say u dotted with v or u dot v, we'll say that that is equal to the magnitudes, the product of those two numbers. So I'm just going to write them next to each other to mean the product, so we don't get confused by dots, because now dot is going to have something very specific. I'll try to make the dot a bit larger, just so we don't get it confused with like the scalar multiplication dot. But I'll also just try to use adjacency, or being next to one another, as meaning we're multiplying these scalar numbers. And this is going to be multiplied by cosine of theta, where theta is the angle between the two vectors. Or, likewise, this is also going to be the product of the x values plus the product of the y values. And when I say it can be defined either way, I mean these two things are equal. Are they? I mean, they look quite different than one another, don't they? So perhaps you have some intuition on this already, but if you're seeing this for the first time, that might be a bit surprising. So let's show, first of all, that those two are in fact equal to one another for the current arena of R2. What's this? And it's really just going to come down to a simple trig identity. So we will let u and v be the way that they are defined on this other board. And let's write out some things. Let's write the magnitude of u times the magnitude of v times the cosine of the angle between them. And let's see if we can't manipulate this expression until we get this expression. Okay, so first of all, we already said that the angle between them is the difference of the two angles as they are made with the x-axis. So let's write it that way. Call this theta 1 minus theta 2. And now it is a trig identity to take the difference of two angles in cosine and write it a certain way. So copying this part that's not going to change much. What is that identity? We're going to have cosine of theta 1 times cosine of theta 2 plus sine of theta 1 times sine of theta 2. And maybe you already see it. Something that looks very similar to what's before. Now, what's the definition of cosine? Remember, the definition of cosine is going to be the length of some adjacent in a triangle divided by the magnitude of the hypotenuse of that triangle. But hey, wait a second, we've got some triangles right here. I've got a triangle here. I've got a right triangle here. And so the cosine of angle 1, get this part copied. The cosine of angle 1 is x1, the length of the adjacent side, divided by the magnitude, which is the magnitude of u, times x2, which is v plus y1. Now, sine is the opposite, right? So we're going to take the opposites, again, divided by their appropriate magnitudes. And then what are we going to do? We're going to just distribute this into each term. And you can see that it will cancel the bottoms completely, and we actually do wind up with what we wanted. The product of the x values summed with the product of the y values. Okay, well, that's good to know. So what is one of the things that the dot product is actually good for, right? Why do I think it's so important, right? Well, for one thing, the dot product alone can tell us whether two vectors are orthogonal. And we remarked a little bit at the beginning of this video about how sometimes it's important to know if two vectors are at right angles to one another. So let's just write it. Perhaps this could be a theorem or a lemma, but I'll write it as a theorem or something like that. Let's say that u dotted with v is equal to 0 if and only if, so this is a biconditional, right? It means that this one implies what I'm about to say and vice versa. U and v are orthogonal. And specifically here, we're really talking about this definition, this first definition. This one is for u and v not equal to the 0 vector. I include that little tidbit because this one doesn't really make sense in terms of the 0 vector. The 0 vector is not pointing in any direction. Its direction is undefined. So what would it mean to have the difference between them, right? Like there's no difference between something undefined and some given value. So in that sense, we could still, however, think about the 0 vector in terms of this other component-wise definition, where it's just 0, 0 that goes here. But then you could easily see, if 0 goes in for x1 and y1, this whole sum goes to 0, right? So the dot product of 0 with anything is 0. And so in a certain sense, that would mean that 0 would be orthogonal with every vector, if this is true what I'm saying. Okay. So let's kind of walk through how you might go about thinking about this proof. But I think that at least a little bit of it should be obvious from the first definition. So in the case where they are not orthogonal, and by the way, it seems a little weird to say that the 0 vector which points in no direction is orthogonal to all vectors, but that's really just a convention. It's something that we mean that the dot product is going to be equal. It's not in the sense that something which points in no direction can be perpendicular to anything. So let's get that out of the way. But right, if we're talking about u and v non-zero, so let's play in that arena a little bit. Right, then their magnitudes are not 0. And if their magnitudes are not 0, however, the product of their magnitudes and cosine of the angle between them is equal to 0, well, that means that cosine of theta must be 0. But when is cosine of theta going to be equal to 0? Well, it's going to be when theta is either equal to, pi over 2, or 3 pi over 2, or even better, let's just say pi over 2 plus or minus k times pi. where k is some integer. And is this not what orthogonal means, right? If I have pi over 2 or 90 degrees to something, okay, we're orthogonal. If I am at 3 pi over 2, well, then you're all the way around over here. Then you're orthogonal. And if I keep going around by 2 pi or by pi, I keep hitting these points, these directions, which are at 90 degrees to some original thing. So yes, in fact, this does show it. Because this also goes both directions, right? If this is true, then cosine is 0, then this term is 0. But there's an additional way that we could see it from the other definition as well. So let's erase this and let's consider that one, right? Because we also have seen perpendicularity or being orthogonal or being at right angles to something before when we dealt with slopes of lines, right? So recall your algebra class, right? When you have two lines that are perpendicular to one another, and I'll draw them right now as lines through the origin for simplicity, right? Right, and let's say this was had a slope m1 and this had a slope m2. Then if they were at right angles to one another, you knew that one was equal to the negative reciprocal of the other. So perhaps something about negative reciprocals is going to come up and show us that we actually get a zero dot product. And in fact, that is exactly the case. So let's say I have some u, and he has x1, y1, and some v. And this is y2, x2. Then if they are at 90 degrees to one another, so here I have, just to be very specific, right, this is the coordinate form for my u, and the coordinate form for my v. Oops. Then they are orthogonal, so u and v are orthogonal if and only if the slopes of these as parts of lines are orthogonal. But what would the slope of the line passing through these vectors be? Well, one would be y1 over y2, or y1 over x1, right? Rise over run. And then we would have the negative reciprocal of the other slope, which would be y2 over x2. But that, of course, if we just flip it and multiply, is negative x2 over y1. So omit the middleman here and cross multiply. Oh, sorry. Y2. If just cross multiply now, and this will be true if and only if your y1, y2 is equal to negative x1, x2. But that's true if and only if x1, x2 plus y1, y2 is in fact equal to 0. So there you have it, two different ways of seeing that this is actually a true statement. The dot product will tell us exactly when two vectors are at right angles to one another. But we aren't always interested in, right-angledness. We're also interested in parallelity, which for lines is the same thing as anti-parallelity. But for rays or for vectors, that's not true, right? Being pointed in one direction is different than being pointed in the direction 180 degrees, right? We call that anti-parallel. So we might want to also talk about parallelity and anti-parallelity just a little bit. But we can kind of see that if I have a vector u and it's going the same direction as some vector v, then there has to be some constant that I can multiply by u to get to v. Right? Whatever I need to do. And you can think of it like I could scale down u even to get to u hat. And then multiply u hat by the length of v to get back out to v. So that's in fact specifically, right, the constant that you would need to scale by. It's their ratio. Right? Multiplying u by this ratio will give us v. But in particular, right, it's a constant times u. And notice this is a ratio of two positive quantities. Length of a vector cannot be negative, right? It's the square root of two squares summed. That's a sum of two positives, square rooted, or two non-negatives at least, square rooted. That's a non-negative number, right? And so here we must have that c is greater than 0. And likewise for anti-parallelity, let me just write, this is w. So we would say that u and w are anti-parallel. And we would also be able to say this exact same process to say that w was equal to the negative of this magnitude ratio. I'll let it be part of your praxis to flesh out that additional piece of information, but what I'm really trying to drive at here is that you have a constant times u is equal to w. This is what it means to be anti-parallel, and we would know in this case that c would have to be negative. It would have to flip the direction of u. Now we could also typify this in terms of the dot product. So the dot product would tell us that in the case of, let's say, perpendicular, right, we have the dot product of two things is 0. In the case of parallelity, we would have that the dot product of these things was equal to their magnitudes product times the cosine of the angle between them. But the cosine of the angle between them is 0, and the cosine of 0 is 1. Oh, so dot product turns into a scalar multiplication of their lengths as soon as we are talking about parallel vectors. And this shouldn't really be a surprise, right? Because if you think about one-dimensional vectors, that's a vector on a number line, we should probably try to get something very similar to scalar multiplication. Actually, that's really not obvious that you wind up with scalar multiplication in terms of the dot product when you look at one-dimensional vectors, but it's true. So, right, dot product includes scalar multiplication as a special case when we're talking about parallel things. And we also have it in this case. This is going to be true if and only if c or v, right, the vector is equal to some constant, some positive constant times u itself. Okay, and then we also could say this for anti-parallelity. I don't know how you like to write anti-parallelity. I'm going to write it as negative parallelity. And this is going to be that u dot v is actually equal to, well, cosine of 180 degrees is -1. And so you have the product of these two things as being the negative of their scalar product of lengths. And also that's true if and only if you have v equal to a constant times u, where c is now negative. Okay, so here is a way that the dot product can typify being perpendicular, being parallel, or being anti-parallel. But all of these things are in fact not the full expression of the generality of the dot product. The dot product tells you more than that. It can tell you how much of the vector is pointed along with another one, right? In the case where we're parallel, that's like saying it's entirely in the same direction, or anti-parallel, entirely in the opposite direction, or orthogonal at some kind of not tangential, but normal direction to the other vector, something incomparable about the two of them. Maybe those aren't the right words, but let's talk about what else this dot product can do. And that's going to talk about projection. So let me actually use the big board, and I'll try to motivate projection a little bit. Okay. There's a couple good ways to think about what's going on when we talk about projection. But let's even go coordinate independent for a moment here. No axis needed, right? If I have these two vectors in the plane, and now I want to know how much of u points along v. Well, just as if v was an axis, I could think about dropping u at a 90-degree angle to v and saying, well, this much of it, this much of u is now pointed along the direction of v. And we would call this vector here the projection of u onto v. And usually to indicate that, they put v as the subscript down here. So here we have another vector operator. But now it's a vector operator. That last dot product was a function. This is a vector operator bringing us back to another vector. It takes in two vectors. It's probably not obvious, but there's two vectors at the beginning, right? And then at the end of this process of dropping it down, you've got one vector. Okay, so this is an operator, right? Took in two vectors and gives you back a vector. And this is something we could do even if we were talking about the projection of u going perhaps quite a bit differently than v. Maybe it points the other direction somewhat. In which case, we just consider the line that v makes, right? V is part of a larger line. And we consider u as being dropped down at 90 degrees onto that line. And then this would be my projection onto v of u. And this would just tell me that u is actually pointing, this component of u is pointed in the opposite direction of v. Okay. Well, perhaps let's just notice two very important special cases that we've already talked about. What if they are parallel? Right? What if u is right on top of v? Well, in that case, there's nowhere for u to go. You drop it right down, it's already on v. And so this would be equal to its own projection. What about the case where they're at 90 degrees to one another? Oh, well then a 90-degree projection, right, drops this straight down onto v. Oh, well, didn't go anywhere. It's, in fact, the zero vector. So projection sort of has those two previous cases of parallelity and orthogonality as subsets. But here we want some way of getting a new vector instead that is scaled appropriately and directed along v to show me how much u points in the direction of v, or what portion of u is sort of pointing in the direction of v. Okay. Now, one way that we could develop an expression for the projection of u onto v is to talk about first the length of that line. So let's develop that. Let's say that we have a v, we've got a u, and I'm dropping it down right onto v. And now all I really want to know is how long is this thing? Well, now this is no longer even a vector calculus question, right? This is simply a trigonometry question. You want to know about how long that is? Well, how long is the hypotenuse? It's the magnitude of u. And what is this angle between? We'll call it theta. It's the angle that we talked about in the dot product. It's the angle between the two vectors. And that is controlling exactly how much of the projection is oriented along v. And so by, trigonometry, well, let's give this guy a name. This is often called the scalar projection. And it's a function of these two vectors. Right? It gives me a number back, not a two-dimensional vector, but a scalar value gives me a scalar value back, which we'll call comp, the component of v, u. And just by your basic trigonometry, this is the magnitude of u times the cosine of the angle between them. Hey, cosine of an angle between, well, that sounds like part of the dot product. But of course, now it's missing the magnitude of v, right? This isn't v magnitude times u magnitude times cosine. It's just the u magnitude cosine part. Okay, so it's a piece of the dot product. And what is it really telling me? It's telling me how far, what is the magnitude of this projection? Another way you could think about projection is sort of like in terms of a shadow. If you were to shine a light above you so that it was radiating directly down, like here was the sun. That's a weird sun. Oh well, that's the sun for now. And you were to shine light directly down onto you so that it cast a shadow directly down, like it's high noon, right onto V. Well, this would be the length of your shadow. Now, let's use this idea that we now know the right length of that line to figure out what the magnitude of the vector should be. And that's all we have to do, right? We know what direction it's pointing in. We already know. It's pointed in the direction of V. So something about V tells me everything I need to know about the direction of this projection. I just need to know the magnitude. Okay. All right, so let's keep going with that idea. So first of all, let's recall the dot product. If this thing looks so much similar to the dot product, let's think about how similar it could really be. V dot U is magnitude of U, V times the magnitude of U times the cosine of the angle between them. And from that, we get that my component of U in V's direction, or the scalar product of U onto V, is going to be dividing this to the other side. We see this is the comp V of U, and so we have that comp V of U is equal to this expression, V dot U, divided by the magnitude of V. But we could, this is just multiplying by the reciprocal, and we could associate that with V alone. So this is V hat dotted with U. Oh, Okay, so it's almost like what you did was you figured out what is v hat. What is v hat? And v hat, you then took the dot product, and that amount, that scalar value that you got, is this component here. Okay. All right. So we're really close, because if I want to know how to scale v by this much, right? If I want to know what is the vector, what is the projection onto v of u, right? Then all I have to do is take this amount, which is, v dotted with u over the magnitude of v, and I need to scale v hat, which has length 1, by that amount. If I multiply by that amount, I'm going to get something that's a vector of this length. And hey, that's projection of u onto v. So what do? We take this scalar and we just scalar multiply it by the unit vector v hat again. So there's a v hat here. There's also a v hat here, right? This is going to be v over magnitude of v again. And so very often, the scalar parts of this are just lumped together. And we write this as v dot u, which is a number, divided by the magnitude of v squared, because there's 2 of these in the denominator now. And then we multiply, scalar multiply, we scale v by that amount, and that is our projection. That is our vector pointing along this direction. And you can see we actually get, I'll let you kind of work this out, that we actually do get all of these results in the special cases of parallel and anti-parallel and perpendicular, all vis-a-vis this v dot u that's on top here. The dividing by the square of v's magnitude just makes this the appropriate length that you do really get projection. In that case, it's the vector that is this long. Okay. So that's all I wanted to say in this video. Let me give you some homework. Math is nothing without practice. Hence the name of this channel. So I'm going to list for you some good properties of the dot product, right? Things which might help simplify some formulas later, things which might be useful as you think about what the dot product is. This is your praxis. This is your practice. This is your homework. I want you to try to prove the following. And that is to say, show why they're true. These are useful properties. Let u, v, and w be vectors. And you can think about them as vectors in R2. And let c be a scalar. A real valued number. Then we have the following. If I take a vector and I dot it with itself, what do I get? I actually get its magnitude squared, its norm, its length squared. Can you show it? Number 2, show that that the dot product is commutative. It doesn't really matter what order I did it in. And that should be kind of funny, because we defined it as a difference of 2 angles, the angle between them. But what does difference have to do with negativity? What does negativity have to do with cosine? There's your hint. Okay, number 3, it's distributive. If I take the dot product of v and w plus w with u, then what I get is the dot product of each one individually. Perhaps think about writing these out in terms of some components for v, w, and u, make them up, and show that each side is equal to the other side. That's good enough for a proof. Number 4, it's associative with scalar multiplication, and I mean that in the following sense. If I take a scalar multiple of u and dot it with v, that's no different than taking the scalar multiple and multiplying it by the dot product of the two vectors. And in fact, I could even pass it into v if I wanted to. And in this sense, there's no matter about who I'm scaling, the dot product, u, or v. You get the same number no matter what. Finally, let's show, and this will perhaps be an easy one if you write it in component form. I think I even touched on this already in the video, that this is the scalar product, that the dot product of a vector and 0 is just the scalar value 0. Okay, that's it for the video today. Next one, I will try to cover dot products and projections and a new kind of product, which is not commutative, called the cross product for R3, three-dimensional vectors, and perhaps we'll even touch on some n-dimensional vector stuff in the next video. Okay, hope to see you there. Have a great one, and stay stoked.